I'm Brad Yohe.
I'm Luke McHale.
I'm Micah Boswell, and we are ECE 4534, Group 4, Spring 2011. Our assignment for this project was to track trains going around a model train layout. Here we have a model train layout. The goal of our project is to create a system that accurately displays the location, speed, and direction of all of the trains on the track at all times. In order to do this, we've split the project up into 3 different parts. The first part, we have sensors and a circuit that listens to the train controller. The second part of the project is an algorithm that runs on a processor that does math to track train location and speed. And the third part of the project is a display on a laptop that graphically displays the positions of all of the trains on the track. The part that I did was the sensors and the interface to the train controller. So we have 4 infrared sensors on the track, here, there, and there. They all connect to a custom circuit board that I designed that has a microcontroller on it. The microcontroller pulls all of the sensors and sends that data on to the processor in the next step of the project. There's another microcontroller that interfaces with the train controller to listen for commands that are sent to the trains for train direction and speed, as well as the direction of the switches or turnouts on the track.
The second part of our project was the tracker, and that runs here on the Spartan board. Tracker takes information from the sensors and from the train controller, and it keeps track of where on the track the train is, which segment between whichever sensors it is, and it computes the position and velocity of the train, and this information is used to display the train on the computer screen.
My part of the project was to take that segment that Brad did and convert it into display segments. So on the laptop there is a program that will display the track layout and the position of all trains on the track. To control the trains on the track, we use a device called a Digitax DCS-50. The DCS-50 allows you to select the locomotive and any switches on the track and control them. And the switch through a solenoid changes on the track. The train itself is controlled through the speed knob. All commands are sent across the LocoNet through the phone cable here. Then goes to the LocoNet receiver board. The receiver board has an adapter which goes into the UART of the PIC, and the PIC then translates that and sends that across the I2C to the S3E tracking thread.
Hi, I'm Micah again, and my part of the project was to build infrared sensor pairs and interpret data from the train controller. The sensors we're using to detect trains are infrared sensor pairs. Each sensor pair consists of an emitter and a receiver, and the emitter projects infrared light at the receiver. Here we have 2 of the infrared sensor pairs, one here and one here. We have 2 because there's 2 segments of the track right here that we need to detect the train on. Here I have a train, and you can see that as it passes this point on the track, it goes between the emitter and the receiver here and breaks the beam, which causes this receiver to send a different value to the microcontroller. One of the issues with these infrared sensors is that a lot of things emit infrared light, such as the sun and fluorescent lights and things like that. So the method we use to reduce interference from other sources of infrared light is called modulation. And here on the oscilloscope, you can see the modulated signal that's going to one of these emitters. Basically, the little infrared LED that is the emitter gets turned on and off at 38 kilohertz, and the receiver looks for that specific frequency, so it basically tunes out all of the other frequencies that could cause interference with the system. The 4 sensor pairs are all wired up to this custom PCB, printed circuit board, that I designed and built. There are 4 wires coming in here from the emitters and 4 wires coming in here from the sensors. Each sensor has 3 wires coming from it because it needs a power ground wire and a signal wire for the actual sensor state. The emitters only need 2 wires, essentially power and ground, but it's slightly more complicated than that. The sensor data is interpreted by this PIC microcontroller, which reads input pins to detect the sensor states, does a little bit of math with it, and then forwards that over an I2C bus, we call train bus, to the Spartan processor, which does the actual tracking.
Alright, the tracking algorithm is designed to track an arbitrary number of trains starting in the first segment here and going around the track in either direction. Each train's position is described by a segment number and the offset from a certain train track junction from the counterclockwise or clockwise direction. This information, along with the velocity and direction of the train, is transmitted to the display so the display can draw the train on the track. Some basic assumptions made by the tracking algorithm is that the simulation is actually a little bit ahead of the physical train. This is necessary because as each sensor needs to maintain its schedule for sensor triggers, we have a train passing a turnout, and that gives us information on where it's going to arrive next. If the simulation is not ahead of the physical train, and a train arrives at a sensor prematurely, i.e. the simulation would be here, and a real train is up here, which is way off, but if that happens, then we can't compensate for the difference because we don't know that that was not an erroneous signal. The algorithm maps a sensor trigger to the train ID by a process that traverses the track and locates which train is scheduled to arrive at that sensor. If all trains are moving in the same direction, this is a pretty straightforward process. It's just a one after another type schedule. If all of the trains are not moving in the same direction, then this process is not so straightforward. Each sensor trigger must identify which train is closest to that sensor at the time of triggering, how quickly each train is going, and whether or not any of the trains are stopped. Preliminary testing of the algorithm focused only on the state transitions, i.e. where is the train on the track with respect to the segments, the sensors, so on and so forth. We spent a good amount of time trying to accurately calculate where exactly is the train on the track at any given time. What we did was take a message off LocoNet and use that to approximate the speed of the train. The Spartan board would drive the polling of the sensors, and at the end of gathering data would send a termination message to the tracking thread. At this time, the train tracking algorithm would go through a single time step, and this would predict a new position for the train. Initially, we used a linear scaling just to approximate, which is not very good. The second step was to actually build in compensation code into the algorithm. So if a train is meant to arrive at a sensor, or it gets there too quick or too slow, you have to adjust the speed. And it turns out that after doing this, we got a pretty good detection algorithm, so we could have a train go around the track, hit the sensor almost right on, and have it triggered. Now the only drawback to doing this is that you have to run the train around the track several times at any given speed to detect that. So we decided instead to take this and figure out how quick the train was going for, say, 6 different LocoNet settings. And so we were able to detect those ranges and assign it a predetermined value that would give it a good approximation for how quick the train was going. So after we did this, our final step was to take our original measurements for the LocoNet speed ratings, which in reality was a curve that looked something like this, which was approximated so. Which used thresholding and a linear scale. What we did was we could take each segment for LocoNet message, which was I think something like 6 parts, and for each fragment we'd have a piece of this linear approximation along with an offset value that we determined empirically in the previous step. So this actually would give us something that was closest to what the train would actually achieve. And so at the end we were able to take one train or multiple trains and using the dial on the DCS-50 scale forward or back the speed of the train and have it go around the track and do so with convincing level accuracy. And that's how we track the trains.
Hello, again, this is Luke McHale. I did the display portion of this project. The tracking thread on the S3E then sends the UART thread each train's position and velocity data. That velocity data is then sent across UART using RS-232 to the laptop. The laptop then receives this information and confirms back to the S3E. The display is drawn using a series of arcs and lines. Each arc and line corresponds to a segment along the track. The train position is defined by a segment and an offset from the start position of that segment. A similar algorithm is used to draw the train position on the track. The train position is noted as a red box, which is simply redrawing a part of the track depending on where the train is along a position. And as you can see on the display side, there is a map of the track and a red dot which signifies each train's position on the track. Track is displayed at runtime and then the train position is overlaid on top of the display. And when I start the train, you can see the train move around the track. So it catches up to the sensor and waits for it. As it runs, it will learn. Adjusting the switch position causes the train to take the inside track versus the outside.
And that's how we track the trains.